sure you can hear me online.
Hi, everyone. Welcome to our third seminar, maybe fourth, an early seminar of the semester. This is Dr. Rachael Kroodsma. She is an assistant research scientist with ESSEC, working at NASA Goddard Space Flight Center with the Precipitation Processing System. She joined ESSEC in 2014 after receiving her PhD from the University of Michigan in atmospheric, oceanic, and space sciences. Her research interests include microwave radiometer calibration and remote sensing of the atmosphere. As a member of the Global Precipitation Measurement inter-calibration working group, her primary work focuses on developing inter-calibration techniques and monitoring the calibration of the microwave radiometers in the GPM constellation. She is also an instrument scientist for the Airborne Conical Scanning Millimeter Wave Imaging Radiometer, which will participate in the upcoming IMPACTS campaign. Let's welcome Dr. Rachael Kroodsma.
Thank you, Kazi. Thank you, everyone, for showing up here. So, title of my talk, as you can see, is called Creating a Consistent Microwave Radiometer Observation Dataset for the Global Precipitation Measurement Mission. So, as you all know with research, you don't do anything on your own, so there are a lot of contributions in here from the GPM XCal team, which is what, if you don't know what that is, I will describe that in my talk as we go along. Okay, so brief outline. So I'm going to give a brief introduction to GPM. Most of you probably know what it is, but you may not know some of the constellation radiometers that are part of the GPM mission, and so I'll spend a little time talking about that. We'll go into what the GPM XCal team is, who we are, what we do, and how we do it. And then I'll talk about some examples of things XCal has done over the past several years since the GPM Core Observatory launched, as well as some recent stuff we've done, and some specific issues noticed with the radiometers in the constellation and what we've done to correct it. And then finally, I'll talk about some recent work that I've been working on with some colleagues about applying looking at application to GPROF, which is the level 2 operational precipitation algorithm with GPM, and looking at some of the effective calibration on precipitation. So first, introduction to GPM. So GPM is an international satellite mission to provide next-generation observations of rain and snow worldwide every 3 hours. And so the way they do this is back in 2014, so February 27 of 2014, they launched the GPM Core Observatory. And so that carried on board a microwave imager called GMI, as well as a radar, dual frequency radar. And so, that's where, yeah. So this, you can see the track is the scan of the radiometer, and then that's the precipitation radar there. So something that even I tend to forget sometimes is when I say GPM, it's not just talking about one satellite. So the GPM Core Observatory is actually the satellite, but GPM is comprised of a whole bunch of different satellites, and so it's this international mission, and so it consists of a constellation of international satellites carrying microwave radiometers, and that's how we're able to achieve 3-hour revisit time, since you're not able to do that with just one satellite. So as I said, I don't know. Most of you have probably heard of GPM, but you may not be as familiar with a lot of the instruments that make up what we call this GPM constellation of radiometers. So we have ones that are current, so ones that are currently flying, and then ones that are in the past. And so here I'll be calling things by imagers, which are conical scanners, and you might also hear me mention sounders, which are cross-tack scanners. So these ones in black are all ones that are currently up there right now. The ones in gray are ones that we have incorporated into this constellation, this consistent data set of microwave observations that we've created, but they are past. They're no longer in operation. And here just shows a typical, just one orbit of each of the radiometers that are currently flying. Just shows the precipitation rates from that. So you can see the good coverage we get, whereas if you just had, this one here is GMI, if you just had that one orbit, you can see just the lack of the global coverage that you get versus if you add in all these other instruments to the constellation. So here just shows a different way of showing these radiometers over time, and it shows this on the right here shows when it launched, and then basically when the satellite died. And you can see the various tracks, and here on the y-axis is it's the local equator crossing time. And so most of these satellites are sun-synchronous orbiters, so they're launched in an orbit where they'll view the same local time everywhere. Sort of it breaks down as you get closer to the poles, but at the equator it will view the same local time. But over time, if they're not, if it's not in a controlled orbit, some of these you can see are really flat. So like these are the MEDUP A and B satellites, like the NOAA 20 SNP. We're put in a very stable orbit, so it sees the same local time. But otherwise, you get these other ones that drift over time, which is something that to keep in mind when you're analyzing precipitation or doing calibration. You want to know what local time it is, since obviously the precipitation can change depending on what local time you're observing. Okay, so here is an image. Once you put all the radiometers together, this is just an IMerge image, which I actually have a video which better shows what goes on here. So I really like this video because it shows what happens if you just have one satellite, and so we'll let it play. And so this shows if you just have one satellite, the coverage you get, as I mentioned, with GPM. And then you add in all these other constellation instruments, and then you can see the coverage that you start to get and why it's really important to have this constellation. I think it kind of starts to speed it up and basically gets into, so this is, if you've ever seen like these IMerge videos, you can download them online. They get shown at every single NASA Hyperwall presentation on GPM. And so here you go with the animation. So this is called IMerge. It's just a video of various IMerge images, and so that's the level 3 product. That's, you know, it's like our most popular, the GPM most popular project. Yeah, so IMerge is created from the GPROF algorithm, which is the microwave radiometer, and then they fill in gaps with IR gauges. There's a whole lot more to IMerge that I don't. Sorry. So the radar is used to basically sort of train like the GPROF algorithm. It creates the database that gets used in the GPROF algorithm database. Okay, and this image I think I took from, was it September 2? So that's Orion right there, as it's probably pounding the Bahamas and heading towards Florida. And then NASA releases animations of when GPM flew over Dorian and stuff like that. So okay, so that's basically an introduction. So now I'll go into like what is XCal specifically. So we refer to ourselves, we call ourselves XCal, or like the XCal team. And I'm a part of it. So our full name is actually, we're the GPM Inter-Calibration Working Group. And so we're within what is now called Precipitation Measurement Missions, PMM. It's what used to be called like TRIM Science Team, GPM Science Team. They put it together, and we're part of the PMM Science Team. And we are responsible for level 1C inter-calibrated brightness temperature files, and then those are what get input to the operational precipitation retrieval algorithm, which I mentioned was GPROF. And so what we do, so this is some of the past activities that we've done since the launch of the GPM core satellite. We assessed updated calibration for the reference sensor, GPM GMI. That was our primary thing we did in the first several months after it launched, is we really looked at the calibration of that. Then we focused on intercalibrating all the radiometers that were currently in operation at that point, 2014, 2015. Then what we did is after TRIM was decommissioned, about April 2015 was when TMI was turned off. We went back and we redid some calibration for that, released a final version, version 8. And then we inter-calibrated trim TMI to GMI. And then we also went back in time and we got all of these other radiometers that were in the past that existed during the trim era, incorporated those into what we call our GPM constellation. And then we even went farther back to the first SSMI in July of 1987. And so that creates a consistent database of microwave observations dating back all the way to 1987 that you are able to download from the PPS server. And so other things that we do now, I mean, most of our work and our effort is kind of past, and now the XCal team used to be bigger because there's a lot more responsibilities for us. Now we're a little bit smaller of a team, but there's still things to do like incorporating new sensors. So we incorporated the NOAA 20 ATMS when that was launched, so that's part of the constellation. MEDUP-C was launched several months ago, and so we've recently been looking at that so we can incorporate that into our constellation. And then just other ongoing things, always good. We need to quantify uncertainties. We're improving our techniques. Always good to do documentation. I put a paper at the bottom here. This was our main paper that we came out in 2016 that talks a lot about our techniques that we use and everything XCal does. So why inter-calibration? I talk about this. So we have here on the left just shows a graphic of a whole bunch of different radiometers, and they're all on different satellite platforms. And so they're built by many different agencies as well as many different countries. And they're all launched at various times and can be in different orbits, is what I mentioned. Also, there's radiometer design differences. They observe different, they have different frequencies, polarizations, Earth incidence angle, which is the angle it looks at on the Earth. And so we need to factor in all those things and come up with a consistent database. And so to do that, we need to identify a calibration standard that all other instruments are intercalibrated to this standard. I like to think of this, sometimes I explain it like clocks, like watches. Like, you know, nowadays not many people have analog ones anymore, but your phone just automatically, you know, calibrates to the standard. But say if you set your clock at a certain time and it's exact, and then you find out several months later it's drifted by like a minute. So that's kind of like, you know, it's drifted over time and then you need to correct it. Or if you say just you always set your clock 5 minutes fast because you want to do that, that would be like an offset. If it could be really stable, but it's not very accurate. It's always at an offset. And so it's always, you know, it's like 5 minutes fast. So that's kind of essentially what we're doing with these instruments, with these radiometers. You have something you know that's accurate. You have this calibration standard. And you have all these other instruments that could be drifting in their calibration over time. They could be very stable but offset. They could have other outside factors that influence them. And so we want to make sure that they're all accurate and they agree to the standard. And so the GPM GMI was an extremely stable instrument, and a lot of the analysis we did after it got launched basically proved the fact that we believe that is it's like the most stable imager is what we'd say at least. And so that's why we use that as our calibration standard, and then we intercalibrate all the other ones to it. Okay, so here's, I mentioned some like design differences with frequencies. So these are typical microwave frequencies here, and I've put them in these various columns. So you can see around 19 gigahertz, GMI has an 18.7, TMI has a 19.35. So similar, slightly different. Different enough that it makes a difference in your observations and you have to account for that. Other things here, this is the water vapor channel, so you can see 23.8 versus 21.3. You have some very different ones. You especially get very different ones here at the 150 to 166, and then you can see all the differences there. So that's something that we have to take into account. So as I mentioned, the level 1C data set, so this is what, this is basically the time. These are various instruments and then sort of the time series that you're able to download from our, from GPM. So we've got 31 plus years, 14 conical scanning window channel imagers, 10 cross-track scanning water vapor sounders. Very high quality, as I mentioned. We intercalibrate to GMI. Version 5 is our current version we're using. And we focus on developing a lot of really good corrections, and I'll show in a little bit some of the corrections that we came up with. And people have actually used this for many applications beyond even precipitation. Other people download the data for things beyond precipitation. So ways that we do this. So how do we develop this high quality level 1C data set? So as I mentioned, we come up with inter-calibration numbers for it, as well as we'll analyze the on-orbit calibration of the instruments. So this on-orbit calibration is necessary to correct for various factors that can occur post-launch with these radiometers. So, you know, you take your instrument on the ground and you test it, you calibrate it, you do as much as you can, and then you launch it. And sometimes there's just things you can't account for pre-launch. So you'll get some solar intrusions. So sometimes, like, the sun just happens to be at an angle and it heats up your instrument, and you get some issues with that. It's just something that you try to account for it. You try to put things around, like a shroud around certain instruments to protect it from the sun, but sometimes the sun just gets in there. Attitude offsets, maybe something was slightly mounted a little, you know, half a degree off. Half a degree is huge. We can see it once it gets up in the air. Some scan biases, obstructions at the edge of the scan. Emissive reflector, something we noticed with TMI. I'll mention that later. And then, as I mentioned, just calibration drifts. Just over time, the instrument kind of as it degrades, it just kind of loses its accuracy, its calibration. So those are the stuff that before we can even intercalibrate the radiometers, we want to make sure that individually the radiometers are as accurate as can be, first of all. So we try to look at a lot of these things for each of these individual instruments, and then once we determine that that looks good, we then go forward with the intercalibration. So some common intercalibration methods, and there's a lot more people that do this beyond just the XCal team. The XCal team is just specific to GPM. There's a lot of other people that you can find other papers. NOAA does it a lot for their NOAA instruments and MHS and everything. So there's a lot of other people in the community that do this outside of us. But these are just some common methods that a lot of people use. So matchup, so you can see here if you've got two. So this blue is like one orbit of one instrument. This green is the orbit of another instrument. And then you can find basically where it matches up within some reasonable space and time limit. Now, you know, what space and time limit you use kind of depends on how accurate, you know, it's looking. Maybe you can do like, you know, 1 degree latitude and longitude in 30 minutes, and that might be accurate enough. Some natural targets. So you can look at, here's an example of, for one of the channels, I forget what it is, it might be 37 gigahertz. It shows an example of what brightness temperature is what we're measuring with these microwave radiometers. And so there's certain areas over the Amazon, so the rainforest here in the Amazon, as well as some of the rainforests in Africa, just looks really stable at our microwave brightness temperature. So it just means like over time, you don't see a lot of variability in both diurnal, seasonal. It's just fairly stable. And that has to do with just the Amazon canopy. It's just really thick. And our microwave observations, they can't really penetrate through the canopy, and they mostly see what's on top, and it's pretty stable. Stable ocean targets where you have low water vapor, low wind, those are also good targets to look at. Antarctica has also been looked at for a lot of radiometers. Unfortunately, GMI doesn't see it, so it hasn't really been used for GPM much. And then also just comparisons with radio transfer models. We've had someone in our XCal team used ARM sites where they launch soundings, and you can get a really good atmospheric profile. We look at reanalysis fields, radio occultation is what some people have used. So as far as like steps that we do for intercalibration, so an accurate algorithm takes into account design differences, as I mentioned, frequency, Earth incidence angle between the two radiometers, as well as geophysical variability. So we first find a stable reference point, so cold ocean, warm Amazon. Step 2 is we account for design differences in geophysical variability. So we have to use a radio transfer model that will account for the geophysical variability, as well as frequency differences in between the radiometers. And then finally, we calculate this intercalibration difference, which we call the double difference. So this is a little bit better way to think of it. So we've got two radiometers, radiometer A and radiometer B, and we want to make them consistent with each other. So we take the radiometer A, the observed data, and we get an observed brightness temperature for that. We take simulated data that comes from a radiative transfer model using reanalysis inputs like MERA, ECMWF, ERA, and accounting for simulated with the correct frequency, polarization, Earth incidence angle. So we get an observed and a simulated, and we get what we call a single difference from them. We take the difference between the observed and simulated, as well as the single difference. Repeat this whole thing for radiometer B, and then the difference of those two single differences is what we call the double difference. And so that's when we I'll refer to some things like single difference and then also like double difference. So that's where that comes from. So here's just an example. I put this in here just for people who may not be familiar with microwave radiometers, like what they look like. So this is example GMI, and it just shows these are just scan lines. I think this is like Australia, something like that. I forget exactly where. But you can tell this is land, this is ocean. And so we go all the way from 10 gigahertz up to 183 gigahertz. And so this sees the surface, and then you keep going higher in frequency, sees more of the atmosphere. And so what we have to do is we can't just use the same exact, say, inter-calibration algorithm for all the frequencies. Or you can try, but we have to make small modifications in it because not all frequencies are, they don't all see the same thing, and some can be a lot more. We've had issues. I don't put this in this presentation so much, but just with simulating some, like the 89 gigahertz channel, there's just some more error in there because it's more sensitive to water vapor and some geophysical variability, and so it means your radiative transfer model has to be like better. And so we just had some more uncertainty in those channels because it looks different. So here's typically like what it looks like, our double difference, what our like inter-calibration looks like. So we come up with what we call cold end values and warm end values. And so going back to this, as you can see, there's cold, so cold brightness temperatures here as well as the warm brightness temperatures. And so we actually come up with numbers at both the cold and the warm end. And then we assume a linear interpolation between them. And we assume that because we assume that all the instrument should react linearly based on the components, the response to temperature. We have had some cases where we think there is some nonlinearity. It's a lot harder to derive a stable inter-calibration constant in between these two ends. We've been looking at various cases, but this basically just equates to your cold ocean, low water vapor, low wind, rather stable. This is the Amazon rainforest there at the warm end. But in between is all various cases. So, water vapor fluctuability, like rain, all this other stuff that's just harder to model. So it's harder to find a point in between that's stable, which is why we have this cold and warm. You can also see we have several points at both the cold and warm end. So we have several groups within the XCal team. It's not just one person doing all of this. And so when we get consistency among them, which you can see, we're fairly consistent within some level of error, it gives us confidence in the results. OK, so moving into examples of what XCal has done. So before I talk about that, I talk about like ways. So how do we determine if an instrument is calibrated well? So we have to slice and dice the data in various ways. And so there's lots of ways we do this. So typically we'll start with 1 year brightness temperature observations. That's just helps to, if there's any like seasonal variability, it just kind of like averages some of that out. So it's always good to use a year. So we split that into each channel, so frequency and polarization. Within that, usually we'll do ascending, descending orbits. Sometimes, this is usually how I start with. So ascending and descending just means is the satellite traveling south to north is an ascending orbit. Descending is north to south. The satellite's traveling. And I do that sometimes because if there are, say, sun issues with where the sun's shining, your satellite changes the way it's looking and where the sun then shines on the satellite. So it can tell you some things sometimes. And then we also divide into scan position. And scan position is just, you can see GMI here, the scan. It scans a conical path on the ground, this arch right here. And so there's GMI has like 221 scan positions. Each radiometer is different. So, but once again, kind of like with the orbits, based on where it's looking, you can tell some things about the calibration, and so we'll split up into scan positions. Other things that we filter the data into, yaw position, if applicable, so GPM, GMI, and TRIM, both the satellite yawed. The time it yawed varied, I think it was like several days, a month or so apart, is that it yawed. So if applicable, we'll filter it into that. Sun position, as I mentioned. Time since eclipse, I'll mention that later. That just has to do with, mostly it's a factor for like GMI and TMI when the satellite comes from behind the Earth, when it's in shadow, and then when it comes out from in shadow and the sun's shining on it, we've had issues where, you know, the satellite heats up, certain issues. So I'll talk about that. Daily and monthly, if stable, we'll look at time series. So for like calibration drift as well as latitude, we can split up into. So now I'm just going to go into various examples of what we did. So this is actually long, 5 years ago, a correction we did. So after GPM GMI launched, we extensively looked at the data, and so we saw some of the things we saw was a magnetic anomaly as well as a long scan correction. So as I mentioned here, what this actually shows is I filtered the data by yaws. So I did a yaw 0 and a yaw 180, as well as I filtered it into ascending and descending orbits. And what that basically told us is based on where the satellite, like the direction it was looking in, it was being impacted by Earth's magnetic field based on the direction that it was looking in. So what I did here is I took the difference. So this SD, that's my single difference. So that's observed minus simulation. And I took the difference between those at ascending, descending, and then split up by yaw. And so you can see the blue ones are a previous version. And that's, you know, in between those two, say for here, the 36 channel, that's a 1 Kelvin difference, which is big between those. Like we always say we'd love to get our calibration down to less than 0.1 Kelvin, which we manage for some cases. Other cases, it's a bit more difficult. But you can see then with the version when this was corrected, the green lie much more closely along the 0 line there, which means the anomaly is taken care of. As well as here on the right, so this is filtering into scan positions. And you can see this here, like at the end of that would be like a scan obstruction near the edge of the scan that was corrected, and we want to see a flat line. You can also see these, like, the line's a little thick, but there's like wiggles in the 183 channel that were also corrected in the version after that. So these are the types of things that we look at, and ultimately, like it was David Draper from Ball Aerospace who did a lot of work on this, and we don't just like to see like, oh, okay, so there's some correction here. Let's just get rid of that somehow. Let's just take the difference and, you know, get out of the data. We like to go back and we like to see, okay, what is causing this? Can we come up with an actual physical correction, not just you know, a correction based here, like, oh, let's just take that difference out. No, we want to go back and actually determine, oh, that was the magnetic field. Okay, now are we actually able to come up with a physical correction for that? And so that's what we like to do rather than just, you know, sort of taking it out. So here's some other stuff. SSMI's calibration drift. The SSMIs each had their own have their own issues, and so this is some of the things when you look at over time. So once again, I filtered into ascending and descending orbits, and then you just look over time. You're like, wow, this goes from +5 to -5 Kelvin. There's an anomaly there. Same thing with F17, and then you look at F18, and you're like, wow, that looks really good. So these are things we want to say, okay, we have to go in there, figure out what's wrong. So one of the things we worked on for F17 is here's another way to filter the data. So I originally did ascending, descending. Now you filter it into sun elevation and sun azimuth angle. So you know exactly like what angle the sun's pointing at. And so these colors mean brightness, temperature, anomaly. Now you look at that and you compare it to the mean reflector temperature, and you're like, wow, that's really similar there. And what that basically means is that there's you have some kind of an emissive reflector on your radiometer, that it's not perfectly reflective. And so based on how hot the reflector is that impacts your observations. And so you can see that here. And so we come up with a correction like this, and then we apply that to the brightness temperatures to basically remove some of the anomalies that we see. Now going back, as I mentioned, we went back after trim was decommissioned. We went back and we updated a lot of TMI corrections, really extensively spent a lot of time updating TMI to really make it good. So version 7 was the previous version before the final one we released. And so on the left here it shows, this is another way to look at if your geolocation is correct, if your instrument is pointing where it should be pointing. So I took the difference between yaw 0 and yaw 180 because they're different, completely different look angles. And so you don't want to see coastline. So obviously you can tell that's South America right there in the 10H channel, which means that there's something off in your pointing. And so what we did is we actually looked through a lot of data, discovered that there was a slight, what we believe, mounting offset in TMI on the satellite. Because we had the PR, the precipitation radar, on board to also tell us how good the attitude of the spacecraft was. Well, TMI still had some sort of like attitude offset after we accounted for any spacecraft offset. And so we determined there must have been some mounting offset that also shows up in the scan position. So that's another way when we look at you know, a long scan correction. We saw consistency between what we were seeing with this method as well as this method. And so we backed out a mounting offset from that. And so you can see here in the latest version, the coastlines basically disappear. And then on the right just shows scan biases. We were able to, we updated the previous version slightly. I know it's a little blurry, but detail, I have paper references throughout if you really want to know more details. So here, another thing, TMI, my colleagues at the University of Central Florida, who are also really involved in the XCal team, did a lot with the emissive reflector. So as I mentioned, time since eclipse here, this shows a brightness temperature bias as it's in shadow behind the Earth, and then it comes out from shadow behind the Earth. So the sun's on it now, and it starts heating up. You know, this shouldn't happen to your instrument. And so these are things that they need to take care of. And so we come up with like correction tables that we put into the data to correct for things like that, time varying thing right there. Okay, so then kind of going, as we went along in time, I said we did GMI, we did TMI, and then we went back in time and decided to do all the instruments that existed during the trim era. So SSMI had 6 different SSMIs on different platforms. And so we went back and we said, can we update some of the corrections we did previously? Because every time we get, every time a new instrument launches, like say GPM, GMI, we learned a lot of things about how to analyze instruments from that. And so that's why we went back to TMI and said, we learned stuff from GMI, let's apply these corrections to TMI. Same thing with SSMI. We learned some things while analyzing GMI, TMI. Let's go back and try to make SSMI even better. And so we did stuff with the along scan correction, made a little bit better. As I mentioned here again are these like coastlines that appeared in our previous version. And then this was the updated version, which you still see them a little bit. SSMI was just not as great a stable of an instrument. And so there's just some things that we can't completely correct for, and that's what I said. We like to get down to, you know, less than 0.1 Kelvin calibration. That's not always possible for every single instrument that we do. And so some instruments we say, well, that looks pretty good for that instrument. Like that's the best we can do for that instrument. I mean, these things, the first one was launched in 1987. We're using instruments that were built in the 1980s, and we're trying to get them on the level of GMI that was built in the 2010s. It's just not completely possible, but we're doing, you know, we try to do the best we can. That's what we did. And so here's just updated inter-calibration. I just included this black line was like our previous, and then this gray line was our updated. So we didn't change it by a lot, but so overall these like inter-calibrations tend to be kind of averages over time, and so you don't see small minor changes like what we might make to the geolocation, which these these would have an impact on, you know, pixel by pixel if you're looking, maybe not so much sort of an average overall, which is kind of what these show. Here's another thing we did. So as we went back in time and we got SSMI, we went back and we got the NOAA MCB instruments to bring those into. Now, NOAA MCB instruments also have a lot of issues associated with them. So this is looking at, you know, a time series of calibration over time. And you can see here on the right, I've got like the 183 gigahertz channels that some like the blue, which is NOAA 15, are just super noisy, super unstable, versus the other ones that are fairly flat, which you like to see. So, so this is something we look at. We didn't spend a lot of time coming up with corrections for these. There's a lot of other people that work with NOAA that have actually done some good corrections with these. But we did use some of this information to be like, okay, so we're not going to use some of this data because it's just too noisy to use. And so that's what we did with that. Now also, some of the more current stuff we've done, so this is some of the stuff that we still make sure we watch for. So NOAA told us that they were doing a calibration change with the ATMS on NPP, and so we had to change our inter-calibration constants that we use. So, you know, here's the change, and you can see right there where it changed in March of 2017, and so we redid our calibration constants and put that in. So that's just some of the stuff that kind of like ongoing, like what we currently do, as well as adding a new instrument. So NOAA 20 ATMS was our most recent instrument we added into. So we have, as I said, our XCal team has kind of dwindled to a few of us. So that's me, Wes Berg at Colorado State University. He's the head of the XCal team. And then Tom Wilhite is still, he actually works with ESSEC, and he's still working with us, helping us out. He's got decades of knowledge, which is great. He still helps us out. So it's mostly, it's like kind of us three. Some people at the University of Central Florida still help us out. But now it's mostly like monitoring of instruments, adding in new instruments. And so we've still got three of us. And so that just shows like numbers here for each channel. These are the numbers we come up with. And you can see, you know, standard deviations are pretty low. So we still want to have, you know, more than one technique that's doing this so that we can either corroborate other people or say, hey, you have an issue, and we've had that where someone's like, oh, you're right, I found the bug in my code. So it's always good to have more than one person coming up with these numbers. So that's what we're still doing these days, even though we've basically gone back in time and we grabbed all the radiometers and inter-calibrated them. We've still got some stuff we're working on these days into the future. Other stuff we look to watch for. Recently, METOP A MHS is channel 2, so the 157 gigahertz channel. This is the NE delta T, so just like the noise. It's just going up and going off the chart. So these are things just to watch for, and they're just things we have to be like, does this have any impact on the precipitation, and do we set the channel to missing? Because that's what we will do as the XCal team. We say if this is an issue, if this is going to impact the precipitation algorithm, we will then say we'll set it to missing. And so these are just things that we still need to watch for. When instruments go bad, when channels go bad, we have to say, okay, set that channel to missing, because sometimes we'll see it if we're looking at the precipitation algorithm. We'll be like, oh, this, I think it was like a year or two ago, someone saw it in IMerge, like IMerge went crazy, the level 3 precipitation, because someone was like, wow, the precipitation looks terrible here. We backed it out to one of the radiometers that was going bad. And so that's still stuff that's important to watch, because a lot of the current satellites we're using in the GPM constellation, they're getting old. They're over, I mean, they're past their like normal lifetime. And so it's going to become even more important in the next few years to really monitor them and see what's going up with them so that they still stay good. So these are all just the numbers of the calibration constants we've come up with for all these instruments. So as I mentioned, we did a cold ocean scene, and then a warm vegetated scene in the red. And these are just tables of numbers. So you can kind of see the comparisons between them and the differences. It's not as important to like really look at them carefully. And then these are all the calibration different MCBs, SSMISs, the MHSs, ATMS, all that. So those are all numbers that, that we've come up with. So in the brief time I have left, I'll see how much of this I can get through. So this is some of the work I've been doing, working on lately with some colleagues. Velko is in here, Yale Yu here at ESSEC, looking at some impact of the calibration on GPROF. So basically our motivation is XCal, we've intercalibrated all these radiometers, and we're assuming that we're actually having a positive impact. But we haven't really looked at the precipitation and say, okay, is what we're doing actually, like, does it matter? Does it have a positive impact on making the precipitation agree among all the satellites? And also it's like, could there be calibration errors that propagate into the precipitation? If we look at the precipitation, can that tell us something about how well we've calibrated? Or maybe it can tell us something like, hey, this looks bad. Could it be due to the calibration? And so, so that's what I've been working on lately. So basically attempt to determine if any differences in the calibration or differences in the precipitation could be due to the calibration. So here's just something to keep in mind how GPROF, the precipitation algorithm, uses the various channels. And so I have some channels it doesn't actually use, like with ATMS, it doesn't use some of these lower frequency channels or 2 of the 183 gigahertz channels. Other ones for like GMI has these higher frequencies that are only used over land. So if you see differences over ocean versus over land, it could be due, you know, different channels have different impacts. I'll have a plot later that shows a little bit more like that. So this is a paper recently submitted that mentioned Yale Yu led the effort on this, where he did comparisons of the GPROF precipitation of all the constellation sensors with the precipitation radar on GPM core over matchup locations. And so those are just a bunch of histograms. Here's kind of a bit, this is where he brought me on board with his study, because he said, this is the correlation over here on the top. This is the correlation of all the instruments with the GPM radar over ocean and then over vegetation. And the main thing here is that he said, so over ocean, as we expect, the sounders don't do as well, because as I pointed out here, so these are the sounders, ATMS, MHS. They don't have these lower frequencies, and those lower frequencies are what's really important for getting precipitation over ocean. And so they don't do as well as the imagers that have the lower frequencies. And then the SSMISs do better. Then AMSR2 does a lot better, maybe because it has it has a 10 gigahertz channel on it. But the main thing that was the concern was here. These are the 3 SSMISs, F18, F17, F16. And while F18 and F16 give similar correlation over vegetation, the F17 is much less. And so it was kind of like, why is it so different from the other ones? Could it be due to calibration? And so this is where we've started. We don't have a full answer yet, but we're trying to dig into it and figure out if it's due to the calibration, can we fix it? So one of the first things to look at here is, okay, so which channels impact the precipitation for SSMIS? So what I did here is I said, okay, I'll add a Kelvin of brightness temperature to all the channels everywhere and just see what the impact on precipitation is. So I did that for each channel. So added a Kelvin to 19V, kept all the other ones the same. Added a Kelvin to the next channel, kept all, and continued on. So what this shows is that this is mean precip rate change. So over ocean, the lower the frequency, the higher the impact a calibration offset in that has on the precipitation. Over vegetation, 37 gigahertz vertical polarization and the 91 vertical polarization has the largest impact over vegetation. So if we're looking at what could cause a difference in the precipitation among sensors over vegetation, we're like, those channels might be what we want to focus on to see about calibration differences. So one of the things I said with F17 that was different, we set that channel to missing in mid-2016. As I mentioned, there was high noise on it, NE delta T on it. And so we set that to missing just because of that. We didn't want it to impact the precipitation. Here's just a plot showing, you know, it's stable over time, and all of a sudden it jumps up to be like 4 or 5 Kelvin, which is really high. So, well, so what happens when you set an important channel to missing that matters over vegetation? Here's the precipitation histograms for all the SSMIS sensors on the left for the year in 2013 when all the channels were working on F17. Now in 2018, when the 37 vertical polarization was set to missing for the full year, F17 is this, the red line there. You can see a difference with the other ones at like high precipitation. And so we thought, okay, maybe that's causing this like difference we see. So what happens is when you set a channel to missing, the GPROF algorithm can't use it. It has to use the other channels. And so what I did here on the bottom is I said, okay, let me add this 1 Kelvin to each of the frequencies and see what happens if I have all channels versus I set the 37 gigahertz to missing, like what F17 is. So, so this darker green is the impact of all channels, basically what I showed before. And then what happens when you set the missing, the 37V to missing, 91V means it has a bit more of an impact, as well as some of these other frequencies have a slightly larger bar there, you can see. So they try to compensate for the fact you have this missing frequency. So, however, that only seems to be part of the problem. Our study, as I mentioned, is ongoing. So some of the next steps that we've determined is trying to create like a pseudo channel and rerun the algorithm, see if that can like have a good impact. Maybe reassess the 91V channel calibration, since that seems to have a really large impact on it. And then just some other things in general for XCal is drive uncertainties for inter-calibration with some of that. So I'll just go into my summary here. So as I mentioned, GPM relies heavily on its constellation of microwave radiometers, and XCal exists to intercalibrate those radiometers to create the consistent data set. We've also done, as I mentioned, extensive work on analyzing calibration of the GPM constellation. So a lot of the work focused on GMI, TMI, and then also as well as the SSMI and SSMISs. Future work, so as I mentioned, we're going to still monitor the current instruments, make sure they still all look good. We added new constellation members. Quantifying uncertainties is what we're also currently working on. Always want to improve our current algorithms, see if we can make them better. And then just working with GPROF to improve the calibration of the sensors. So that's all I have. So thank you for your attention. I'll take questions. Kazi's got the mic, so to make sure people hear it online, can wait for her to.
Very good talk, Rachael. I have a couple of questions. How do you deal with differing scanning geometries, or all your instruments have the same scanning geometry, the way they scan? Oh,
yeah. I mean, so we incorporate that into the radiative transfer model, essentially. So, I mean, we know the incidence angle that it's looking at, and then so that gets incorporated into the radiative transfer model. Does that answer that question in terms of like scanning geometry?
Yeah, I mean, when you compare two instruments.
Yeah. I mean, so essentially, the radiative transfer model should take care of, say if you've got a cross-track scanner and it goes all the way from like 0-degree incidence angle up to like 50 something. Essentially, your radiative transfer model, if it's accurate, it should account for all those different angles. We have noticed there are maybe some errors in that, and so we do for a cross-track. If we look at a cross-track and we compare it to a conical like GMI, sometimes we will filter the look angles of the cross-track so it's similar to what GMI is, just to kind of help to eliminate any errors that could be associated with the radiative transfer model not perfectly modeling it.
And you mentioned that you are going to monitor instrument your summary like that. Is it like you're going? Do you do it in real time or like monitoring of? You do it just for study and then you.
We do have well, so we do have some like real time, like Westberg at Colorado State. He has a website. I could have like put the link on here or something that kind of monitors some stuff real time. We don't. I think that's something that is probably like we should do more often. Like I mentioned, there was, I think it was the NOAA 18 instrument when that went bad. We didn't see it until it got into IMerge because we weren't necessarily monitoring it like first, you know, looking at the brightness temperatures. So probably something we can still
I mean, in
improve
G6,
on.
I mean, you have given very good deliverables and like the coefficient, the calibration coefficient that you. But the real-time monitoring would be really.
Yeah.
very
Well,
good.
yeah, and I know like we've mentioned that with G6 before, and sometimes it's like, well, yeah, I mean sometimes it can be hard to know if the calibration like changes, you know, like on a day, like because it's just in terms of how stable it is when you look at it by day, like daily. But yeah, I know it's like I think a lot of times sometimes we'll go back in maybe every like few months and we're like, oh, it still looks good, like with certain calibrations of things. But yeah, but that's also like I showed the plot of like NOAA has these real-time. This, yeah. I mean, NOAA does. I put the website here. They do this for all their
This is yeah, the ICVS, but like real-time inter-calibration.
Yeah, we don't know because yeah, I guess I didn't mention that with our inter-calibration constants. Most of them are calculated, like say for the GPM SSMIS instruments. We did this back in 2015, so they're from the year 2015. And we haven't like really updated the numbers because we assume.
No, I meant about the biases.
Yeah, like so like those biases they're from back in 2015 and we don't like monitor them real time necessarily. So. Yeah.
Thank you, Rachel. Really nice talk. Packed full of information and really clearly delivered. I'd like to talk about climate in terms of being able to find climatic change of precipitation. Do you think that calibration is getting to the degree that we can do that kind of thing, or do we still have a long way to go?
I mean, I would hope so. I mean, that, like I said, it's some of the older instruments, even though we've, you know, we try to calibrate them as good as we can, like there are still more issues with them than like, you know, if all our instruments were as greatly calibrated as GPM GMI and just as stable as GMI, like it'd be great. But I don't know, like I don't work with a precipitation algorithm as much to know exactly like how stable do you need your radiometer to be to, you know, to see really changes in the precip.
Fair enough. Yeah, thank you.
Thank you. I was curious, given the number of instruments you have on in your constellation, what's your for a given point on Earth, what's your mean coverage cycle time or period? I would say.
Oh man.
Roughly speaking.
I don't know. I mean, I don't know, and it varies. It depends on latitude and everything. So I don't really know. Like Bob, you have a you happen to know? About 3 hours. That's GPM. Yeah, GPM. Like we say, it's 3 hours. So yeah, now you might know. Yeah, so it's 3 hours. But like, I mean, it's kind
pretty
of
frequent.
You know, if I go like way back, I guess.
Yeah. Oh yeah. Okay. Fair
So
enough.
here, okay, this was, like this is one orbit, so 90 minutes, one orbit, 90 minutes, your coverage in 90 minutes time. And then you can imagine if you kind of, you know, step those over a little bit, you'll still get those nice little like diamond gaps in certain areas. So that's, yeah.
And the other thing I was curious about was, given that some of these or quite a few of these instruments are still on, still have an active team supporting them, like behind them. I'm curious, what is the state of like communication that you might have with those other teams in terms of they're also doing some calibration work as well. Is there communication in terms of comparing results with these teams?
Oh yeah.
Like?
I mean, Well, I know at least we work with David Kunke does a lot with SSMIS, and so he knows a lot of what went into building them and everything, and so he calls in frequently to our telecons and gives us insight into them. And even with some of the NOAA instruments, like Les Berg, who's in charge of XCal, like he keeps a pretty close communication with the people at NOAA. Like they told us they were making a calibration change to NPP ATMS, so we were like, okay, good to know. So we don't just like, it appears and we're like, what happened here? And I mean, definitely with GMI, like we worked super close with Ball Aerospace, it was a really nice partnership we had with them, and that's why we know so much about that instrument, because they like gave us a bunch of stuff. Versus other things, like sometimes with SSMI, like it was hard to find stuff on it, depending on how much DoD decided to release to the public. And so, but yeah, we definitely try with most instruments. We try to, get as much information about their like on-ground calibration and stuff as possible.
So you mentioned the yaw maneuver on the TRIM satellite, and I've been doing the CalVel for the lightning imaging sensor on TRIM, and we also found the similar pattern for the yaw maneuver. I'm just curious because you didn't talk too much about the pitch and roll maneuvers. Do you find like how many percentage offset by the yaw, the roll and pitch maneuvers?
What do you mean the roll and pitch maneuvers for?
Because TRIM also did the roll maneuvers, I believe.
It did. You mean like the deep space calibration?
Yeah.
Yeah, like it did. TRIM could not pitch up. It could not do a pitch maneuver. It could only do an inertial hold. So it was basically more of a roll. I mean, it sort of pitched then, I guess. So that was part of. I mean, I didn't go into a whole lot of detail here. The University of Central Florida did a lot. I mean, a lot of their corrections they came up with were from the deep space calibration of TRIM TMI. I didn't work as closely with that, so I can't give as good of an explanation on what went on with that. But you had, what was the other question about?
Well, I'll just get into the second one. So when you do the yaw maneuver, do you find a latitude or longitude dependence on the yaw maneuver?
For TRIM? You mean kind of?
For TMI.
So kind of like, I guess you were referencing what we had looked at for GMI?
Right, yeah.
So I did something very similar like that to TMI and saw maybe some dependence, not quite as strong as this, in terms of, I mean, that was definitely something, like I had mentioned, stuff we learned with GMI, we were trying to apply that stuff we learned back to TMI. So when we saw this magnetic anomaly, we're like, well, could that exist with TMI too? It wasn't as strong as this, but it was, we did maybe see a little bit of it, and that may still be in the data, things we couldn't fully correct in the latest data set.
Are they corrected in the L2 data?
Well, I mean, in the level, like in the level 1 brightness temperatures, like we've done as many corrections as we could. So. Bob, did you have a question? Okay.
More questions? Cool. Thanks for showing up.
Thanks, everyone.